vector addition, right? And some axioms how they mingle together. What about inner product? You have one more, this inner product structure. So I'm going to call this bracket notation in here bilinear pairing. If it satisfied everything except positivity and definiteness, it's called bilinear pairing. Because those are really easy thing to establish. Positivity, not many of you are able to actually prove them, and I gave you some matrix. So here's an example. V is R3. What kind of inner product space are we looking at? Dot product, right? So we have that, but here's a challenge. That A is now being given by 4 to -3, 2 to 0, -3, 0, and 5. This matrix have interesting property. Do you see that property? Diagonal, across the diagonal, what happens? 2, 2 repeated, -3, -3 repeated, 0 and 0 repeated, right? Okay, it's called symmetric matrix, right, along the diagonal. So this allows us to conclude that if the pairing is given by, you know how to define a pairing, that if the matrix is given like this, and remember? We multiply these two vectors around this matrix. So when you multiply to the right, that's natural. It's a column vector space, right? But when you multiply to the left, you can't multiply column vector in here. So you have to transpose and multiply. Then this is going to be a scalar in the real number. Okay? But so this is a bilinear pairing. I'm claiming this is a bilinear pairing. Positivity and definiteness is hard, but linearity is because of this algebraic structure is obvious. What is the other one? Last one. Conjugate symmetry stuff. Here conjugate is nothing because it's a real number. How about symmetry? If I swap this around, why is that going to be the same? Because of the symmetry property of the matrix. The one that if you swap this around, it turns out the coefficient appears in the other coefficient, but they are the same, so it guarantees that it happens. Does that make sense? So if I write it like this, you obviously easily, observe that this is a symmetric real matrix. Therefore, this is bilinear pairing. That's really easy go. The difficult part is that is this bilinear pairing going to be a positive and definiteness, right? So think about positivity. So what was the question about positivity? If you paired it itself, it's supposed to be positive number or 0, right? So if I choose V to be A1, E1, this is A1 to A3. Here's A1, A2, A3. That's a column vector, right? So column vector goes here. The sideline column vector goes there. Okay, so here the pairing V is going to be A1, A2, A3. Let's see, A1, A2, A3 is here, right? Is a 4A1, 2A2, -3A3. Did I have this right? Okay, so here's a 2A1, 2A2, 0, and -3A1, 0, and 5A3, right? This number, and then this is going to be multiplied here. This is really a dot product at this stage. This first component is multiplied there, second component multiplied there, third component multiplied there. It's really the dot product. You see what happens here? 4 times A1 squared. That 4 came from this. And here's a 2 times A2. What about multiplying this one to that, and we pick up 2 times A2 squared. I'm multiplying this one to the second component, just to collect the squares. This entire thing is multiplied to the third component, so we get 5 times A3 squared. So that came from 4 to 5. 1, 1, 1 in here. So by multiplying this one A2 to A1, then you get 2A1, A2, right? 2A1, A2. This 2A1, A2 came from 1, 2 position. And if you do this one, 2A2, A1, here, 2A2, A1, then 2A2, A1, they come from position 2 and 1 in here. and they're the same, it duplicates. So I hope you agree that you get the square part like this. And these are A1, A2, and A2, A1, right? It's the same things. There's a 4, A1, A2. How about this one? This is A1, A3. 1, 3 is involved. So that's 3, 1 is involved there. So negative 6, A1, 3. How about this one? 0. It's none. So if you actually multiply out, you end up at this one. So this is, if you look at bilinear. So we want to show why this one is greater than or equal to 0, no matter what your A1, A2, A3 is, right? So in this one gets harder actually. It was a lot harder than the early example that appeared in an advanced problem. So here's a new approach that you're supposed to learn. The idea is prevailing idea in this entire section of ortho inner product and rest of the part. So here's how it goes. We want to choose different bases such that this guy is not like this, not A1, A2, A3 mingled together like that. What is good about dot product thing? Dot product is like A1, A2, A1, A1, and B1, B2, A1, B1, A2, B2, things like that. So if you dot it to itself, you end up at A1 squared, A2 squared, A3 squared, and that's it. No index mixing, right? The goal is that can we choose a different basis so that you don't have anything like this. It's all about square, square, square. Then I can conclude that if I don't have these two terms, it's easy. It's greater than 0. All right? So new basis. B, V1, V2, V3, which is not E1, E2, E3, which is usually how this one is represented. Column vector is A1, E1, A2, E2, A3, right? So we're going to choose different bases and put it through. V is arbitrary vector, which is represented by new coefficient like this, correct? Such that if you pair to itself, you want to see the clearer picture than this one. It's harder to complete this square. Does that make sense? So let's do that. So this is a little bit of bilinear, or you can think of it as a dot product. So V dot, not V dot V, V pairing B is A1 V1, A2 V2, A3 V3. That's one pairing, right? And here's A1 V1, A2 V2, A3 V3. And this is real real bilinear pairing, so the symmetry is there. Okay? So look at it as if it is a dot product. This one is dotted with that. So let's think about all the combination. So do you see that V1 dot V1? V1 pairing V1, what is the coefficient? A1 squared. So what other possibilities are there? V1 pairing V2? What do you see? This one paired up with the V2 like that, right? How about this one, V2, paired up with the V1? Because the symmetry of the real, they're the same, so 2 times A1, A2, that coefficient shows up exactly. Is that right? Let's just keep going with a different pairing. Do you see V1, V3? 1 is paired up with that, and 3 is paired up with that, and you see the pattern. This index shows up exactly the same way. How about A2 to itself? Then A2, A2, that's going to be squared. And think about pairing V1 and V2 is paired up exactly. So to what is the next thing, reasonable thing to do? To V2, V3, I think that's it. Right? Paired up. V2, V1 is already done in here. So it's A2, A3. Is that right? Okay. So you see this V1 through V3 is fixed. And then we want to change this A1 and A2, A3 and hope to see this one is something that is clear so that you conclude this is, what do we want to conclude about this one? Positivity, right? So when is it going to be positive? Simplest way is I got square, this is lovely part, A1 squared, right? I can conclude the positivity. A1 squared. I forgot A3, so A3 there is also there. Continuing. v3 and v3, and every other different index pairing is done in here, so I don't cover it. So this is good. These are positive things. These we don't know. This crazy thing can happen, right? So what can we hope for about the v1 pairing v2? We want to choose a very nice basis so that this pairing v1 v2 becomes 0, right? If it's a 0, if that's 0, if that's 0, how wonderful. That's going to be positivity, right? Maybe it fails to be positivity. Then turns out this v1. Another thing is that this v1 pairing v1, and we want this number to be positive as well. If it turns out to be negative, then you prove that this does not satisfy positivity. And this must be positive. This must be positive, whatever that you choose. All right? So that's our goal. You have to go out there and find v1 and v2, v3. These are dimension 3 vectors, such that if you pair it itself, they're all positive, and if you pair it each other, they're all 0. Have you seen that kind of vectors? If it is like in terms of dot product. Do you see the 3 vectors out there dotted to itself in the 3-dimensional space, dotted to itself is a positive, but dotted each other become all 0. Those are typical orthogonal basis, right? The E1, E2, E3. But E1, E2, E3 is here. You rotate it a little bit, and you can still see that that property is still there. So you can see many of them inside a 3-dimensional space. But this is not 3-dimensional space. This is actually it's a 3-dimensional space, but it's not dot product. That's what I meant. Its inner product is given by with this weird thing, right? So here's a naive approach to this. This one goes like this. All right, let my v1, I don't know where to start, so why don't I start with the e1? So I'm going to use this arrow. So if I use arrow in the board like this, it is the 1, 0, 0. Okay? If I don't use arrow, or in typesetting, if it is a boldface e1, it means 1, 0, 0. But if it is just a plain e1, it could be any vector that enjoys that vanishing property when it is inner product paired each other. Okay? In the board, I'm going to distinguish the 2 things like this. Right now, it's going to be v1, so it's not going to be confusing. All right. So e1 bar arrow is the 1, 0, 0. Okay. So what is the first property that we want to hope for about this one? We want to check if you pair them to each other. We want that to be that. So here's 1, 0, 0. Let's see what happened. If I put 1, 0, 0 here, that's the inner product rule. You have to multiply it in here. You see that picks up 4, 2, 3, negative 3. Is that right? 4, 2, negative 3. So here's a 4, 2, negative 3. So let me write down in this way so that you can see clearer. All right. So pairing E1, E1 using that matrix rule is a 1, 0, 0 and 4, 2, negative 3. I hope I did this right. Correct? 4, 2, negative 3. So it's a dot product here. Did you know that dot product is written in this way? To matrix multiplication. It just picks up 4. Right? So we're good? We're good. 4. This is 4 here. It's going to be 4 times a squared. That's good. What if that turned out a negative 4? That we don't know yet. But we're gonna pursue it in there. All right. That's good. So we got that one vector satisfy this one. So let's get v2 such that this one is satisfied. So I have v1 in that. So look for v2 such that what property we have is the first thing I'm going to pay attention is if I need to have this property anyway. This should be paired to 0. Okay. And once I find this one, and then I'm going to hope for whatever that I found is some 0. Whenever the coordinate has 0, it's convenient and easy. 0 in there. There's some positive number. We're hopeful. So what was v1? v1 is 1, 0, 0 still, right? What was b2? We don't know. It's ABC, right? So I'm going to put ABC in there. So let's bring that down so that we can see that easily. So I better copy it down here. This matrix is there. So if I put A, B, C here, you see that 4A plus 2B minus 3C. Agree? A, B, C here. And this guy doesn't matter, it turns out, because I have 1, 0, 0 here. So only thing that's going to survive is 4A plus 2B minus 3C. So it's 4A plus 2B minus 3C. And what is this supposed to be? 0, right? So all I'm looking for is an A, B, C that satisfy this equation. All right, our V1 has 1, 0, 0. It's supposed to be basis, right? That we're looking for V1, V2, V3. These are supposed to be basis. So if I choose 1, 0, 0, why don't I choose, this one being 1, B part, so that it's clearly kind of linearly independent, and hope that, or that's the wrong thing. I'm gonna make A equals 0, so that this part has V1 has this non-zero. If this is A equals 0, then it's clearly kind of linearly independent. But there, there are infinitely many solutions, right? So what BC do you see in the clearly easy one? I would do 3 and 2. That seems like easiest solution there. So I got one in here. V2 is 0, 3, and 2. That'll do it. Okay? So let's do one more thing to check, right? V2, V2. We're going to check that. It turns out it's a positive. So I'm going to skip that part. V2, V2 turns out to be whatever is a positive number. Lucky. We got that positive. If it is not positive, you keep continuing like that. And you'll be able to finish this 0 business, and you end up at negative number. From there, you can perfectly conclude that this doesn't satisfy positivity. And you'll see that. All right. So what is the next step? V3, right? We have to go for V3. So let's see. V3. Let's think about this pairing becoming 0 condition. So we want V1 to V3 should be 0, right? V3 is a new V1 and V2 we already have. So this is a condition. And V3 is compared to what? V2 as well, right? So that should be 0, correct? So what was, this is going to be ABC again. So from there, do you see exactly the same condition we had before? V1 to V2, that's what we did, but we don't know anything about V3. ABC is going to be same, 4A plus 2B minus 3C equals 0, correct? So what about V2 here? What is V2? It's 0, 3, 2 transpose, right? And ABC is there, so that's that ABC is there. So 2A, 2B plus 0. The first one doesn't matter because it's going to multiply to 0, right? What about the third one? ABC, so it's a 3A plus 5C. After multiply ABC, that's the second and third vector. If you do that, it's supposed to be 0. That's this condition right here. Correct? All right. So what is it? 3 times a 2A plus 2B plus 2 times negative 3A, 5C is equal to 0. So that's a new condition like this. This is 6 and negative 6. Is that right? Is that really happening? 3, 6 and negative 6. That's wonderful. And what about this B part? It's a 6B. And there's no B part in it, right? So it's a 10C. Correct? And easy OA is that 3B plus 5C in there. The two conditions kicking in. Is that right? Right. So any ABC that satisfy these two conditions will satisfy this one. So which one better be 0? This one is non-zero there. This one is non-zero there. Maybe I'm going to just make A equals 0. Maybe that's going to be easier. Or C equals 0 or something. Which one is easy, you think? But this is more of the process anyway. I don't think this whole inner product thing is just not recorded. That's my guess. I stopped recording at that test discussion. Anyway, let me go back and finish that up. You found those V1, V2, V3 just satisfying this condition and not being able to control this one, and you end up at this form because at least we got rid of these things. Then you have some negative numbers could be floated around. If this one negative, you choose A20, A30, and A1 to be positive. That is one particular vector. And you stick it in here, that becomes a negative. So you discovered some vector, you're pairing it, is now positive. Therefore, you're proving it, this is not inner product space. If some of them end up at 0, then positivity is going to fail. Not positivity, definiteness. You can create that 1 V1, 0 V2, 0 V3. If you're pairing itself, it becomes 0, but it's not a 0 vector. So once you have that much of information, not being able to control this positivity, you have full conclusion about whether it's inner product space or not. That's the beginning. Inner product spaces often come into this matrix form. It's actually a theorem. Every inner product space can be expressed in terms of this matrix form. Then you can determine whether it's inner product space or not. I was talking about bilinear. All right? And this business, computing this one, and I showed it in an elementary way here like this, is called the Gram-Schmidt process. Did you hear about that in the algebra? Gram-Schmidt process? Right. This is like a first year kind of method, and the book shows that you don't have to do this one. Actually, there's this bilinear pairing method. You don't have to enter this coefficient. You can, there's a systematic way of doing that, which is repetitive use of orthogonal projection formula. Remember orthogonal projection formula? U and V, and if you want to project it to like that. And what was the formula for the coefficient of V? That U kicks in and dotted with the V, and V squared, whatever that is. Then these two vectors orthogonal to each other. This formula shows up repeatedly, so it's fairly easy to understand the process. If you keep repeating it, and you'll be able to find this V1, V2, Vj. So it's always possible to find this one. You can't control this one. Then you conclude inner product or not. All right? So that's where we're heading. Orthogonal basis. The bases that are like orthogonal to each other. Good?